One of the principles, general principles behind good programming practice in general and object-oriented programming in particular is what you can think of as code reuse, or essentially writing everything or all of your algorithms or code only once, okay? And there's lots of reasons to do that, one of which is it's easier for you to type it if it's only there once. More significantly, if you have kind of every conceptual piece of code, functionality, algorithm expressed only once, when you have to go back and change it or fix it or modify it or extend it to do something differently, you only have to change it in one place, as opposed to search through your 50 to 100 pages of code to figure out all the places it appears and change it consistently in all those places. And rest assured, no matter what you write, you almost certainly will have to change it. And so one of the principles that's evolved is to try very hard to write everything down only once. And there's a number of mechanisms for doing this. One is something called, or you can call procedural abstraction, where, say, you have a bunch of places in your code that kind of do the same thing, but maybe slightly differently or slightly different data. One way to abstract is to look at what these things do in common and try and rewrite that all those various pieces of code is kind of a single procedure or a single loop, and parameterize it across all the different uses. All right? So that's one way you can do code reuse, to keep yourself from having copies of things. Another one that's kind of similar is what is sometimes called code refactoring. Now, that's a more general technique. But if you have pieces of code that's commonly used, kind of sub-pieces of code that's commonly used in algorithms all over the place, it's useful to take that common piece, make a procedure or method that expresses that, and then just call it from all of the places that it appears. We saw an example of that yesterday. Somebody suggested this. We had two add routines in our vector 2D routine from yesterday, and if you look at the code, they pretty much do the same thing. Okay, but they differ in how they get the various pieces. Okay, the static one had 2 arguments passed in. This one used the implicit instance argument plus an additional argument passed in. But you could easily implement this one by getting the various arguments and then calling the static one, or vice versa, so that you only do the actual add code in one place, and you basically fiddle around with the arguments in the other case till it's in a state where you can call the common one. For something like addition, which isn't likely to change and is only 2 lines, I wouldn't sweat it, but anything more significant than that, that actually does some functionality, very useful technique to only write it once. And it's easier than you think to end up with multiple copies of the same thing all over the place, because with Emacs, you get an idea, you need to build this thing over here, you cut and paste pieces from all over the place, and then you just end up with lots of copies, and then, which isn't necessarily bad, as long as then you step back and think, okay, what am I really doing here? What are the common pieces? And then pull them together and re-abstract them. So certainly when I write code, it tends to grow as I add functionality, and then you think about the structure that implements this new functionality, and then you can usually shrink it back down to something much more complex or compact and dealable. So, but a third way of handling this code reuse or usability is inheritance, which is the topic for today. Object-oriented languages, and Java in particular, supports inheritance of classes, in particular just to give you this level of code reuse. We talked about how to design classes like our friend Vector 2D from yesterday, which has a bunch of functionality encapsulated in it. And you can certainly, this enforces a number of nice things, nice programming techniques for you, in particular, hiding the implementation, the particular data you use to do the implementation from the expression of what the class does, okay? And it encapsulates and hides a certain set of functionality. That's a good property. What inheritance lets you now do is take some piece of functionality you've built and share it under over a lot of different cases, okay? Java and these object-oriented languages let you build a hierarchy of classes based on what would be semantically or intuitively an is-a relationship. Okay, something is a subclass of something else if it has a lot of behavior of the more general thing, but then some specific behavior of its own. And clearly, if you are able to have a structure that lets you implement it in that way, you can implement all of the capabilities of the general thing, and then on the more specific thing, only implement what's different. And you have, A, you save yourself a lot of typing, and B, you have things concentrated where they belong. So, enough generality. Let me get a little specific so things will start to make sense. Let's say we want to make a new class to represent complex numbers. I hope in your in your calculus class you talked about complex numbers, yes? So complex numbers are representable as points in the plane, okay? They have a real part. They represent numbers of the form a plus bi, where I squared equals -1. And they can be represented as points in the plane where the x-coordinate is a and the y-coordinate is b. So this is cool. So the representation looks a lot like what the vector 2D is. And indeed, if you have two complex numbers and you add them, they add, the real parts add, and the imaginary parts add, which is exactly the formula for adding 2D vectors. So say I want to implement my class complex. I could start from scratch and say, okay, I'm going to have a real imaginary part, a double imaginary part, or a real part, an imaginary part, accessors for all of these parts, and then implement all these add routines over again. I can say, okay, I've got all this in vector 2D, and I want to inherit it down. And the way you do this, the syntax, the magic word in Java is extends, and then the class that it extends. So this actually defines a class called complex, extends vector 2D. You can put it in a file called complex.java, run the compiler on it, and you do have a complex number class all ready to roll. Let's see. Let me further divide my board. For example, you can start to allocate without doing any further work. You can do stuff like this. I'm going to have to write a little smaller to fit this stuff in. And we can call our addition thing on it. And everything is great. We have our complex class, and we automatically inherit all of these routines. So even though this whole body of this is right now blank, it nonetheless will let us inherit the add routine from its parent. It gives you a blank constructor, which is going to call the blank constructor of the parent. So basically, we're going to get a not very interesting complex number when we do this. We're going to get 0, 0, but nonetheless, you know, for that little typing, we get something. So say we want to actually make more interesting complex numbers. We need to add a constructor here. So we do our normal constructor. And I'll put them real and imaginary. Now here's a question, what do we do? We have the real and imaginary guys here that we want to set, but we don't have any anything to set here. We don't have any instance variables that are particular to our class. They're all set on our parent. Now we could think of doing, trying to access them, but since they are represented private, they are declared private, they're still secret. Even child classes of a particular class, something that extends a class, can't see these guys. So we need to do something else. But Java gives you a syntax for explicitly referring to the parent instance or the parent class. It's analogous to the word this, which lets you refer to yourself. And the magic word to refer to parent is super. So the constructor for your parent class is always called by the word super and then the arguments. To me, this is not a particularly transparent syntax, but there it is. So when you build a class that inherits from or extends a given class, and you write your constructors for that child class, and I'll use the word child class or subclass interchangeably. Similarly, the word superclass or parent class for the more general class interchangeably. You want to always have a call to some constructor in the superclass, some super, to initialize all of the parent class's variables. Because even though they get inherited down and accessed in this instance, they are hidden from you. And so you want to call up into the parent's constructor. If you don't do this, it will run the default constructor, the empty constructor for the parent, and in this case give you something that's 0, 0. Okay? So this, since actually in our constructor we don't have anything else to do, that's pretty much it. So in our main routine, let me maybe move my main routine over here. All right, I can now allocate a complex number, give it some values, and everything is good. I now inherit, of course, my getX and getY routines that I can call on this complex number, and it will go and find the routines on the parent class. Now I can add additional functionality or routines to the complex class. For example, complex numbers have an absolute value function, okay, which gives you the absolute value of the complex number. This is identical to the length function, but it just has a different name. So we can go and implement that. Public, and that would return a double. Abs. and all we want to do is return length, and we're all set. Yes?
I'm sorry, back on the constructor. You
Yes.
said you wanted to initialize them, but what have you done? What have you initialized? You've made x equal r equal to x?
Yes. What I've done is essentially super, okay, sort of gets substituted for this. Okay, so this, when I call super on this, it tries to find a constructor routine in the parent class that has two arguments, where each of the arguments is a double. Okay, so it calls the one we did yesterday, where each of the arguments is double. And I've just shown the definitions here, not the implementations. But what this one does is then take this guy and assign it to there, and this guy and assign it to there.
So they'll be 0?
So, well, they start out to be 0, but when I call this, all right, I call it with 3, 4. These guys get set to 3, 4. So these guys are 3, 4. These guys are 3, 4. And this routine sets those guys to 3, 4.
Are they 3, 4 and all the other methods too of the like the
For this particular instance, right, once I've made this instance, if I then do a length call, it will use the values of the parent instance. Whenever you make an instance of a child, you kind of get an instance of the parent class along with it. So in some sense, the instance structures of a child class are kind of its data plus the data for the parent class plus the data for its parent's class, all the way up the inheritance hierarchy, all carried around for you, mostly invisible, but it's all there.
But haven't we sort of eliminated the parent data? And written
You can't see it, but no, it's there. You haven't so much eliminated it because you've essentially just carried it along with you.
But aren't we just carrying along r and I in the child, and x and y are no longer?
Well, R and I here are essentially dummy variables. They're just the parameters that I'm declaring here. I haven't declared any instance variables here at all. Okay? So here I'm basically, I could have called these A and B or anything. These are just dummy variables, and these are the parameters, arguments to the function. And so this is just a function call, which gets substituted with 3 and 4. And eventually, when I call this constructor, the constructor does the assignments. I didn't write out the values of the implementations of the constructor.
Okay.
But,
So they're
okay.
called x and y still in the parent.
Right, they're called x and y in the parent. And if we had made them public here, I could have actually, instead of doing this, I could have done x equals r, y equals I, and that would have worked just as well if I had made these public. Okay, the fact that I made them private means that not even child classes can access them, so we have to do it this way. And
You
yes?
never make them public, right? You never make these things public.
Yeah, you never make these things public. There is something in between public and private called protected, which means that the child class can see it, but nobody else can. I tend not to use that because forcing you to call back to the parent class to do initialization and stuff helps you or encourages you to refactor code, okay, to make sure that anytime there's functionality in the parent class, you don't try and reproduce it in the child class using the parent class's variables. You always call back to the parent class. Sometimes, as we'll see in a minute, it's a real pain, but
Do the constructors always have the same number of arguments for the child and the parent?
they don't have to, no. For example, let's see. Say I wanted to make a class that represented, instead of complex numbers with colors. All right? This is a weird concept, but just bear with me. So, so what I would do there is, since vectors don't have colors, maybe they should, but we have to add some additional data onto our subclass, and we'll make it a string type, and it'll be color, and we'll default it to red. And now we could make a constructor for complex numbers that passed in three things: the real part, the imaginary part, and a string, which was our color. All right. So we need to initialize the parts of it which are relevant to the parent class, which are just the real and imaginary. So we just call vector2d with real and imaginary. And now we have something which is essentially a red complex number. But now we need to initialize our local data, which is only relevant to us. So we would add that in here, color equals C, and everybody should be happy. Make sense?
So I assume you can call the method in the child the same as the parent, and then override the parent's method?
Yes, I could have, if I wanted to, I could have, yes, I can define, say, a length method here that does something completely different. And then when length was called, it would get the local method rather than the parent method. Okay, when you have a hierarchy, and they're usually drawn something like this, vec2d, and then there's an arrow with some kind of arrowhead. There's lots of different notations for describing these hierarchies, and the arrows have various looks to them. But this notation generally means that complex number inherits from vector2d. And so when you call a method, say length, all right, remember, this is a method call here, inside of a method declaration. So when I'm trying to call abs on complex, it says to just go ahead and call the length routine and return its result. So the system's problem is, where do I find a length routine? Okay. So first it looks in class complex and sees if there's any length routine that you define locally in class complex. If it finds one, it'll just use it, assuming it fits the signature, assuming it has the right number of arguments of the right type, returns the right type. If it doesn't, it goes and looks on the parent class. Okay? In this case, vector2d, it looks for a length routine that returns a double, and indeed it finds one, so it uses it. If it can't find one there, it'll look for a parent class of vector2d. All right? And if it doesn't find one there, it will give you an error. And although it does that lookup at runtime, okay, so it essentially checks separately for each instance. It does the check to make sure it's plausible at compile time. So it will always make sure when you call a method inside here that somewhere in the inheritance chain there is one. Most of the time it'll do that check. Sometimes actually it can't. And it'll give you a runtime error saying can't find routine that looks like this. Yes.
If you rewrote a length function here, is there a way to refer to the length in the parent?
Is there a way to refer to? So I believe you could do, right. I believe you can do super.length. Okay.
That's just one parent level up.
Right. Super is analogous to this in that it lets you refer to the parent class.
So is that the same as saying vec2d.length?
That would be the same as not so much vec2d.length, because vec2d.length is actually a static method. Okay? This would actually be an instance method that refers to this particular instance. Okay? Remember, when you extend a complex, when you allocate a complex, you get a vec2d kind of attached to it for free. And it makes a whole new vec2d and assigns it to this complex. So you're actually using that one, okay? So, any more questions?
But what happens if you have only one variable here? You have only public complex double R.
Okay.
Which one will we look?
Well, the arguments to this one, okay, the subclass constructor, are somewhat independent of what gets called in super, right? Here I'm passing 3 arguments into the complex constructor, but I'm only calling super with 2 because my superclass constructor only has 2 arguments. Okay?
Only with one?
If I called super only with 1, then if I had a constructor here that only had 1 argument, it would call that one. We built one yesterday, but I didn't carry it over to today. But if it found one, it would call it. If it didn't find one, it would complain. If you don't give any super, it'll call the one with no arguments, which is always there. All right.
What's the one with no arguments? You said it's always there.
Right. What it does is, it would be called from a program as new vect2d open close with no argument. And what it does is it just gives all of the data members its default values, their default values. So it's pretty uncontrolled, and you should try not to rely on the default. I think it's called the empty constructor often because it has no arguments. Once you get it, and tomorrow's concept, you're like breezing through the rest of the course. But this is the tough one. So we're just going to see lots of this over and over again. Now we can actually add. Presumably we made this complex function for a reason, and instead of just using vec2d, other than renaming things like length. So we can add functionality. And one of the pieces of functionality that complex numbers have over 2D vectors is that complex numbers are a field, that they support multiplication and division. And also some other juicy relationships like conjugation.
Can you clarify the term field?
Field is something that has an addition operation, a subtraction operation, or additive inverse operation. It's closed under addition, closed under multiplication, which means that it has an inverse. And so any 2 numbers, you can multiply any 2 numbers and get another number, or any 2 things and get another thing, and you can divide 2 things and get another thing. The only thing that you can't divide through, of course, is 0. So the upshot is we have a multiplication operation, which let's write one of these. Public. Let me write out the formula for multiplying 2 complex numbers so you can see what I'm trying to do. And let's see if I get it right. It's A1, A2. Right. Let's do that. Let's do that. A1, A2 minus B1, B2 plus the crosswise ones, A1, A2. No, A1, B2. Oh, sorry, right. B2 plus A2, B1I. Oops, and this should be a 2, not a squared. Yes?
If you're calling a method of the parent class,
Yes?
and it uses the private variables, can you access them through that? Because I would assume that the private fields in the parent class are not available to be used in the class that is outside, let it be a subclass.
Well, it depends on what you mean by used. You can certainly,
Available, I mean.
you can't access them explicitly, let's put it that way, but certainly you could call getX, which will return the value of it, okay, or length, which will return some computation based on it. All right, so the methods that you're calling that are implemented on the parent class have access to the parent class data, and you can use the results of those methods. You just can't go in and fiddle with those guys. So, which will turn out to be a real nuisance, as we'll see. All right, so our multiplication routine returns a complex, and we'll make it an instance method, so I don't have to write twice as much. All right, and now I need to compute the new real component. And now I've got to write a long thing. Well, if these were public or protected, I could just access them directly and say, you know, x times y or x plus y. But since they're private, I've got to get at them through the use of our accessor methods. So I end up writing something like get x times this one, which is b dot get x minus get y, and since I like to parenthesize, I have to erase my little diagram here, get y times b dot get y, close. All right, that's the real formula. And notice, in order to get at the various components that I need, I end up calling these accessor routines on the parent class. Now, I don't have to say super dot that and super dot that because I haven't overridden them here. The only ones that are available on the hierarchy are up here. So that's all fine. And I can write out that formula I equals, and I just don't have the heart to do it. So you can translate that into that. And then complex result equals new complex of my new real and imaginary parts, and then I return res. So, and that's my multiplication routine. So once you get through, halfway through writing this stuff out, you start to wish, my goodness, I wish I hadn't made these guys private. And you're often tempted to make them protected so you can access the variables there. And if you do enough of it, you're often tempted to say, you know, screw it all, just make everything public. You regret it later, but it is tempting sometimes. So, questions? Yes?
You could also have said get real and get a mad. Would that improve the abstraction? So it makes
Yes. One thing we could do is say overwrite make a routine called get real.
Yeah, in your hand, you have those.
Right, exactly. And all that would do is call get x. Okay, so in some sense, if we were really implementing complex, we would want to do that just to make the user be familiar with the terms that you're using. So the user could think of complex in terms of real and imaginary, which are just renaming x and y. Let's see. There's some other cool routines we can write on complex. which are, I guess, in the notes, and maybe it's not worth going through them, to type out, well, maybe it is, because I'm going to erase this. It should be in the notes. For those of you who have printed out Lecture Note 3, I have a new improved version, which unfortunately I neglected to mail in this morning, so I will upload it this afternoon. Another operation is conjugation, which basically turns A plus BI into A minus BI. And so that one is really nice to implement. Return, we just want to return a new number, a new complex. Which has components, and I guess to be clean about this, I need to do get x and minus get y. And then since we want to implement division, we need to be able to do division. And one way to do that, I just provided a reciprocal routine. Because it shows the nice power of refactoring once we've done a lot of work building up small routines. Reciprocal. And reciprocal actually doesn't take any arguments, although it is shown to in the notes. The formula for reciprocal is basically the conjugate divided by the length, or the absolute value. So all we have to do that is to first compute the absolute value, then get the conjugate, sorry, I need a variable here. All right. This isn't quite as cool nor as legible as it should be.
1 over absolute value squared. Absolute value squared.
Is it? Oh. Rats. All right. I'm going to do the squared here, so I don't have to squeeze it in. So have that. So now this works, since it's my value. My reason for doing this is to just show that once you've built up these pieces, okay, you can now take a fairly complex operation, and rather than trying to re-expand it out in some horrible formula using all those get x's and get y's, you can then write it in terms of the pieces that you've already written, and it comes out nice. I use the scale operation, which we didn't implement yesterday, but it's basically an operation that multiplies both x and y by a real constant. So it just scales the vector, shrinks it, or grows it. So, okay, any questions till, because we go on to the next issue. Speak now, or?
What code have you saved retyping here in defining this complex one?
Well, the actual thing I'm computing here is A minus BI over a squared minus b squared, right? Minus b squared?
Plus b squared.
Is it plus b squared?
Absolute value is the square root of a squared plus b squared.
Oh, you're right. You're right. You're right. You're right. So this is what I'm actually computing here. And I could have gone through and said, get x minus get y divided by get x plus that. It just works out differently here. And the nice thing is, if I suddenly go back and change implementations, or for some reason you wouldn't do it in complex numbers since they don't change the definition of length very often. But if for some reason the absolute value of number changed, I could change it in one place and everything would remain consistent. When you're dealing with programs involving data structures and the like, where there isn't a mathematical or physical reality that you're implementing, things change all the time. All right.
So did you have, sorry,
Yeah?
just back there, did you have to create a result variable, or could you just say
Oh yes, no, I could have just expanded out this big expression and returned it. After a while, I get confused if my expressions get too complicated. So, basic inheritance. More questions? Yes?
Can you hide the methods from the parent class so that they can't be called through the child class? Because we now have an abs method which basically does the same thing as the length method.
Right.
And both of which are exposed to your programmer over in the main routine.
Right.
Which seems like sort of an abstraction kind of violation.
Well, what I could have done is, for example, made the length routine protected. That way only the child class could use it and implement absolute with it. The trouble with that is anybody who wanted to use your vector 2D class would then not have a length method. So, this inheritance stuff isn't perfect, I guess, is the real model. It helps you do stuff, but there's a lot of cases of things you want to do where you say, this just doesn't do what I want to do. And you're right, it doesn't do what you want to do. All right, the last thing I want to talk about in the remaining 40 minutes is an exceptionally cool property of inheritance, an exceptionally useful property of inheritance. That's called polymorphism. And I just like that word, so. And the idea is, let's see, a simple version of the idea as follows. Java lets you automatically upclass or upcast inherited types. So I was defining complex numbers before and putting them in variables that were complex. Java will let me do the following thing. Okay, allocate a new complex number and put it into a variable which is of type vector 2D. Now this doesn't work in general. If I just picked a random type, like string, it's not going to let me do that. But because vec2d is the parent type of complex, it will let me do this. And then it will let me do any of the operations on C that are consistent with considering C to be a vector 2D. So I can do the length routine on C. Okay, now I've lost my multiplication routine because vector 2D does not have a multiplication routine here. So, but I can do all of the other things that I could do here, just thinking of this as a vector 2D thing. Okay, that's not really the cool thing. Okay, here's the cool thing. And we don't really have an example, a routine here that demonstrates the cool thing. The cool thing is that even though you've defined this guy to be a vec2d, this variable to be a vec2d, Java, when it allocates this thing, remembers that it's really, deep down, a complex number. Okay? And so if, say we had our old favorite routine, toString. All right? And say we had implemented a toString routine. This would have been actually a really good example. Why didn't I think of this before? A toString routine on vector 2D that print out the following. Say it just printed out the string x comma y, where it substituted x and y for the numbers. And say we wrote one on complex that printed out x plus bi. Okay? So you can imagine how to do this. It would be a little bit ugly, but you can imagine. So we have a toString routine over here, and on our complex implementation, we have a toString over here. The cool thing, and the essence about polymorphism, is if we do c dot toString, this is going to give us as you will notice, that should have been a y. It's going to give us this version of toString, the one on complex, even though the variable that we're calling it on is, we declared it to be a vector 2D. Okay, so this is a really cool thing that somehow Java remembers, like Lisp, Lisp has, or Scheme has runtime typing. It remembers, it knows the type of all of the things that you are referring to. Java also, for classes, has a runtime type system. It's remembering, as you create things, what type they really are. And so even though it lets you refer to them as a vector 2D routine, it's going to go get the right one. Yes?
Is the advantage of this so that you can do vector or matrix operations and heterogeneous types with the same superclass? Is that, or is there a reason?
I guess the advantage of is part of what you said as yes. The advantage is that you can write routines. Say you just wanted to write a print routine for a bunch of things, and sometimes it was going to be given vectors, sometimes it was going to be given complex. When you wrote your print routine, you didn't want to have to worry about what all the different types are. You just wanted them all to do the right thing. Okay? You could define this, if this print routine was defined, or this toString was defined everywhere, your routine would just work, which is the beauty of it. toString in fact, is defined everywhere. A little digression, but we have our complex type, our vec2d type, there's a global supertype called object built into Java. And every new class that you define that doesn't inherit from anything else implicitly inherits from object. Okay? The consequences of this is that anything can be cast as an object. You can make a variable of type object O equals new, and pretty much any class thing that you put there, it's happy with. Okay, object is just the most general class. And there are actually some functions that are provided on object, which if you don't override them, they're still available to you. And one of them is actually toString. So if you make up any class, don't write a toString routine and try and print it out. Print line, for example, will call the toString routine, and it'll print out something like class 32, or something very unuseful, but nonetheless there. But as a consequence, if you overwrite the toString routine on your particular routine, all of the system functions that call toString will go and find your toString routine for your class and always print out your class the way you beautifully asked it to. You will see that in the polynomial class example on the problem set, if you hadn't seen it already. So, any questions on this concept? I'm going to work through an extended example to the extent that I have time, but.
I don't know, the way it's hitting me is that somehow you've avoided using constructors with the child complex. Is that true or not true by doing this? Object.
Well, I have called a constructor on the child class. Complex is the child class, yes.
It already exists.
Right.
It already has constructors.
Oh, yes, this is assuming that the stuff I erased already exists. We haven't gotten any magic. I just ran out of board space. I'm sorry. So the complex class has existed and implemented. So all I'm able to do here is to create one. And instead of calling it a variable of type complex, I can assign it to a variable of any supertype.
Oh,
Okay?
and the advantage of that is?
And the advantage of that is that I can write abstract routines in terms of supertypes and have them all work for all of the subtypes without me in advance having to know what all of the subtypes are, for example.
What do you mean by work for all the subtypes?
Well, say I had a routine that sorted two-dimensional vectors, okay, according to some algorithm that was consistent with, all right, I could write that algorithm in terms of vec2ds, okay, and then I could call it, when I called it on, say, a pile of complex numbers, it would still work, okay, because it's able to treat complex numbers as vec2ds, okay. That's the point of there. The second point of polymorphism is that if you have something specific, if you override a routine of vec2d with a specific routine on your child class, even if you do that upcast, even if you use a variable which is a superclass, even object, Java remembers deep inside what the true type is, and when it goes to find the toString routine, goes to find the one on complex, not on vec2d. So.
So suppose we had like colors on the complex, could we do the same? I guess we could do the same then.
Oh, you mean add a color here? If I had put that constructor in? Yeah, and you wouldn't be able to from the variable C, since that only has access to the routines that are defined on vec2d, it wouldn't be able to do anything with color.
So now we need to access color.
Right, you would not. You can cast down if I have a vector 2D that I, as the programmer, know is a complex. I can do cast down and say complex D equals, and this is the cast syntax, open parentheses, type name C. All right, so this says take my variable C, which is a vec2d variable, and now variable D, I'm going to take that same data structure, because this is reference assignment. These two are pointing to the same object in memory, but now I'm going to treat it as complex, and D now has access to all of it has access to, say, the multiplication routine. I can say D dot mult. Now, since we only have one, we'll multiply it by itself. Yeah?
If complex's toString function also printed out the color in some form,
Right.
Then even though the vec2dc can't ever do anything with the color,
Right.
when we call c.toString, will it print it out
Yes.
using the colors that the
Yes.
underlying complex has?
Yes.
Well, what about
if C was a pure vec2d, could we cast it down also?
No. You could write this because the compiler doesn't know in advance what is going to end up in that C variable. But then when you try to do it, okay, and this is why this is a dangerous thing to do, unless you're absolutely positively sure it's going to work, what's going to happen is at runtime you'll get an error that'll say illegal cast, and your whole program will stop. Or we'll talk next week about how to catch errors and keep it going. But
what was the illegal cast?
Oh, well, say I did something like vec2d a equals new vec2d. Okay, I just got a new one of these guys, and then I tried to cast it as a complex. Okay, Java remembers that this one really is a complex, but then this one really isn't a complex, and when you try and cast that one, it's going to run into trouble, and it's going to say, I can't do this. But unfortunately, when you're writing the code and compiling the code, there's no way ahead of time to check whether that's going to fail or succeed. So when you do downcasting, which you will have to do under lots of circumstances, you have to be either very sure that it's the right class, because you wrote the code so that only things of the right class can get down this path, or you have to be prepared to handle the error when it happens. There's mechanism to do that. Or you can actually ask the class what its type is. And so there is a bunch of mechanism, which I probably don't want to go into today, called reflection, which lets you ask instances about themselves. You can ask instances what type it is, what all of its parents are, what methods it supports, what data it has. There's routines that will give you all this. So you can use that to check if it's the right type before you then try and use it as the right type. It knows that it's building complex, so it basically essentially tags the actual instance with the type. Okay? It tags it with a complex. It probably tags it with a pointer to kind of the mother of all complexes. So it can do all this reflection stuff. But every instance has a lot of data carrying along with it besides those, besides these variables which we told it to carry along with it. It's carrying a lot of stuff along with it that tells it the type and what methods it supports and the like. So basically, when Java creates one of these things, when it allocates it, it allocates a whole mess of extra space that it just fills in with information as to what type this piece of data is. So,
but if I were to initialize something that had previously been a float and initialize it as an integer, it just truncates it and throws
right.
Decimal places away.
Right.
And so,
well, there's two different things going on here, remember.
From that complex,
There's two different things. There's the type information over here, which is typing variables. Okay? So, and you're right, here, that's equivalent to this. All it's knowing is the type of this guy. Now, when it does the creation of this, all right, it's creating some piece of memory out on the heap, which it's, storing the fact that this is a complex, and then it's storing any local data for the complex, and then it probably stores either immediately or a pointer to its kind of parent, and then it's storing the x and y of the parent. So when you get a complex, you really get some big old thing like this. I mean, I have no idea if this is the actual representation that it uses, but this is conceptually what's going on. So as long as you have a pointer to this, the first thing that's there is the fact that, hey, I'm a complex number. And so no matter who is pointing to it and what they're calling, what type it is when it thinks it's pointing to it, okay, it always knows it's a complex number. So it's just carrying all of this stuff around. Yeah.
I mean, you mentioned going deeper into the implementation. Are we going to sort of really explore, I don't know, vector table type stuff, or how Java sets all these sorts of things?
No.
Object relationships.
Yeah, we're going to stick to how to use the stuff rather than how it's implemented. In one lecture later on, we'll talk about how to do object-oriented programming in C and C++. And in C, you've got to implement, if you want to get this functionality in raw C, depending on how much of it you want, you've got to implement it by hand yourself. And we'll talk about how to do that as a function of how much pain and effort you want to go through. All right, I still have some time, and it'd probably be worthwhile to go through another example. So the example that I want to do that I started out here is expression trees. All right, what I want to do with the expression trees, or what expression trees are, is tree structures to evaluate arithmetic expressions. Say I have 3 plus 4 times 2 plus 1. All right, and I want to compute that value, or I want to make a program that'll compute general values of this type. And the way you would really do this is, it would be input as a string. You would parse the string and create a tree structure, then evaluate the tree structure. We're not going to worry about the parse part. We're just going to worry about the tree part and let somebody else deal with the parse part. What you would get out of the parse part is a tree structure that looks more or less like this. Internal nodes would be tagged with operators, and they would have child nodes. So each, assuming the whole thing is binary, each top node, each internal node would have an operator and 2 descendants, or 2 child nodes, which would, in this case, also be. And then finally, you get to your numbers. Okay? So this is an internal data structure, very, very abstract, of what the expression tree would look like. Okay? If you were writing a compiler, you would do something very similar, but on a much grander scale. You would take the whole text of your program, all of the expressions and statements and everything, come up with some gigantic tree which represented that, and then you would grovel over that tree and either execute it or turn it into lower level code or rearrange it. So the first thing we want to do is come up with how we can represent this in memory. All right? And so we need things which represent each one of these nodes. And I have sketched out a structure over here, a class, which I call expernode. All right? I'm not going to write out all of the implementation, but because it's pretty straightforward. But an expernode is some structure like this. And we're doing it pretty abstract level. So all the properties we have on expernode is the fact that it has a right descendant and it has a left descendant, which are, if you are standing on this side of the board, are opposite from where I pointed. Okay, and the 2 descendants are actually both expernodes. All right, so far so good? Okay, cool. Now I'm initializing them to null, and null basically means that there's nothing down there. These guys don't have right or left descendants. They're just the ends of the tree, the leaves. So if I use this constructor, they'll get set to null, and I'll get essentially a leaf node. All right? I've made another constructor where I can give things a left and a right node, and it'll make one of these. Given that I've already made these 2 nodes, I can then make this node. And given that I've made these 2 nodes, I can make, or these 2 nodes make this node, etc. So if I have two nodes, I can make a higher level node that has them both. And one thing I want to make clear, since in object-oriented programming you are overwhelmed with tree structures, this tree structure represents pieces of data in memory, structures, objects in memory, which have pointers to each other. Okay? So this has references. This refers to data members. This is not an inheritance tree. Okay? So this node is not inheriting from this node. There's no inheritance going on. This is just a pure memory picture. Okay? Data structure linkage picture. And they look the same, and it's confusing. And when you get into Windows systems, it's more confusing, but you just have to keep it straight. All right, what methods do we have? We have accessor methods, get left and get right, which return expr nodes. These would be straightforward to implement. They just return this value and this value, respectively. And we have a test method, which returns a Boolean and is called isLeaf. Okay? And what isLeaf is going to do is return true if I have a node with no descendants, and return false if I have a node with descendants. Question? Oh. Also pretty straightforward. This one just tests this one and this one. Okay? Everybody with me so far? All right. So given these things, I can start to construct trees, but once you try and construct this thing, you find there's something missing. What's missing? In this structure that I need to build that. Exactly. I have no way to put actually any data on this. This, I've gone so abstract that this data structure just describes anything that looks like tree structures with two descendants. Okay, which is good. So now I've got a nice generic class that does an abstract function of trees with trees with two descendants or two children. And now I need to subclass it to make it useful in this case. And to subclass it, I need to make some subnodes or some subclasses. And I'm going to make two that are useful to start out with. These guys are somehow different in functionality than these guys, right? These guys have no descendants, first of all, and their values have a number in them, okay? These guys have operators in them, and they're trying to do something. So let's make class, call it opnode, extends expr node, that's expr node. Better yet, if you will bear with me, I'm just going to say en for expr node. All right, I'll say e.n, and you can do a macro substitution in your mind. Ding, 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 curly braces. All right, so once we've done that, we get these two data members for free. We get all these routines for free. So we need only our additional information, which is our opcode. And we're going to make that. How do we represent these plus, minus, whatever? We have a lot of choices. We could represent them as a string. We could represent them as an integer, whatever. The only thing we're ever going to do with them is essentially compare them against each other, so it doesn't matter. We want something that's easy to compare, so I'm just going to call it an int. All right? That's going to represent this operator. And because we are good programmers, rather than kind of arbitrarily remembering that, okay, multiplication we're going to assign to be number 1, that we're going to be 2, plus is going to be 2, we're going to name these things. And in Java, there's not a particularly good way to do this. The way it's typically done is you define static public final cap letters, this cap letter isn't enforced, 1. Okay? So, and we can do static public final times equals 2. All right? So now, say I want to do an initialization, say I wanted to make the default node be plus. I can use plus here instead of the number 1. So all this is really a variable. It's just an ordinary integer variable. Actually, I forgot to say int here, didn't I? I apologize. These have to be typed as ints. So what all these things, this is just an ordinary integer variable, but it's got a bunch of specifiers on it. Static means it's associated with the class rather than any instance. Okay? And final is this magic keyword, means you can't assign to it. The compiler won't let you do any assignments to it. So basically, plus is going to be the number 1 forever and ever and ever. All right? And public just means it's accessible. I have my normal type thing here, integer, which means it's an integer. Well, that's cool. Let me write my other class. Let's see, and now I need a constructor for this. And the op node always needs a left, which can be an expr node, a right, which can be an expr node, and then an int, which is its op. And so we first want to get our node, initialize our parent, so super LR. This initializes the tree node part of us. And now we want to do the op part of us. Op. All right? Minus some semicolons. Are we all set? Cool. Now I need some code to do these end nodes. And I'm going to make a type called lit node for literal node. And that also extends en. It has one additional data member, which is the value that we're going to pass in. And its constructor is going to be lit node. All we want to do here is pass in the value, so int v. And we still have to call our parent, but we're going to call the version that makes us, that has no descendants, and then we're going to set our part, value equals v. Now we're cool. So now we can build one of these tree structures. Let's say, we can say lit node L1 equals new lit node of 3. We can do lit node L2 equals new lit node of 4. Then we can say op node O1 equals new op node of L1, comma L2, comma, and we'll use our static variable syntax opnode dot plus. Okay, what this opcode dot plus means is to, or opnode rather, opnode dot plus means to find the class opnode, look for a static variable called plus, and use that value here. Okay, so this is much better than passing in the number 1, remembering that we defined plus to be 1. It's always good to define these guys as labels. So what we've done here is O1 now looks like this. We've built basically this structure, and basically O1 points to there, L1 points to there, L2 points to there. Are we all happy?
How come you have the value as public?
You want them to be something, and something that you can compare against, okay? Because when we eventually want to do something, we have to remember whether this guy is plus or minus, okay?
Why don't we just keep it as plus or minus?
Well, plus or minus being what? Plus being the character plus, the string plus. Sure, we could use any of those, anything that's distinct. When I'm numbering unique things, I usually use integers. But yes, you could use any of these. You could have defined this to be static, public, final.
That's just an arbitrary selection.
Yeah, it's just an arbitrary selection. It's much easier to handle, to name something to be kind of an abstract meaning, even if you assign it to something like that internally, rather than having to carry around a string type around. It's just an extra level of abstraction. It's not enforced for anything, and it probably would have been even clearer to define this as char type instead of int, and to do that the char plus, the char minus. Sometimes you define an operation where there isn't a good, character thing for it. Cool. So let's work on the last piece of this, which is, now that we've built one of these structures, how do we want to evaluate it? Or how can we evaluate it? And say we have one of these of arbitrary depth. Well, the algorithm is kind of simple. You want to do a recursive algorithm where you say, first get the value from each, if I'm an operator node, first get the value of each of my descendants, okay, and then figure out what kind of operation I am. And then if I'm plus, add those two values. If I'm times, multiply those two values, and return that as my value. All right? So that is nicely recursive, and we can write that down. So let me eliminate my constructor. And I want to write my evaluate routine for opnode. I'm assuming these values are integers because it's shorter to write. Public int. Oh, how do you spell evaluate? There we go. Evaluate. And since I am an op node, I know I have left and right nodes. So all I have to do is, let's see, int v1 equals get left, which is the parent successor routine, which is going to give me that, dot evaluate. So I'm going to call evaluate on my left-hand side. This is a useful but a little peculiar Java syntax where you can first call a method that you know is going to return an object, and then use the dot operator on that to then call another method on the instance that you get back from the first method. It takes a little getting used to, but once you're used to it, it's really handy, saves a lot of typing. If it makes you happier, you can also put parentheses there to make it a little clearer. We do the same thing for the right. And then we do an if. We want to return v1 plus v2. And we'll do else if op equals times return v1 times v2 dot 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 if you have more operators. But that's pretty much it. And that's a pretty nice representation. Over, we need an evaluate node. Eventually, we're going to get down to where the right and left is not an op node, but it's an evaluate node. So we're going to need an evaluate routine over here. On our lit node, which is pretty easy, that's just I'm returning my value. All right. So the only thing I left out of this discussion is, okay, I've got an evaluate routine here. I've got an evaluate routine here, so I have one defined on op node. I have one defined on lit node. Now, get left, all right, even though I'm using this obscure syntax, get left is returning something of type expr node. So what's really going on here is to write that out, which probably I should have. Expr node v n1 equals get left. Okay, and then we have int v1 equals n1 dot evaluate. So here is our polymorphism in action, kind of hidden in here, that we're first getting the left node, which is of type expr node, which could be a leaf node. It could be one of these guys, or it could be one of these guys. But all we have to know is we can call the evaluate routine on that, and it's going to return us its value. And if it happened to have been an op node, it's going to call this evaluate routine and return the right thing. If it happened to be a lit node, it's going to return this it's going to call this evaluate routine and return this thing. So it's just going to do the right thing all the time.
There's already the evaluate under expression node.
Right. Here's
Doesn't have anything. One of that.
exactly. Here's the remaining question. All right. In order for this nice polymorphism to work, in order for me to be able to do this, I need to be able to call evaluate on an expr node. All right. Which means I need an evaluate routine on an expr node, which I wrote here. Okay, so expr node has an evaluate routine. Now, what should the evaluate routine of expr node do? Expr node is very abstract. It doesn't have any data. It can't evaluate anything. You're stuck. You could either wimp out and say, okay, I'll just make it return 0, and I'll always make sure I override it and hope for the best. But Java gives you a more powerful mechanism to keep yourself from getting into trouble, which is this magic keyword abstract. Okay? I've defined it on toString here too, though that's probably redundant. So here I've defined my evaluate routine abstract. What that means is that I'm going to declare an evaluate routine here on my expr node class, and I'm going to call it as if there was an expr node, an evaluate routine here, but I'm never going to provide one for this class. Okay? I'm never going to provide one for expr node. I'm only going to provide it, and I promise to provide it, for all of my child classes. And that has an implication, okay? If I am not going to provide this routine, I'm only going to provide it, say, on my child classes, I can never actually allocate one of these guys. I can never call new on an expr node. Because if I could call new on an expr node, I could then take that expr node, which doesn't have any evaluate routine associated with it, and try and call evaluate, which would break. All right? So Java does not let you instantiate any classes with abstract methods. And in fact, you can tag the class as abstract also. Okay, so if you have an abstract method, I think you have to actually tag the class as abstract. You cannot instantiate an abstract class. You cannot call new on an abstract class. The only thing you can do is make child classes fill in the missing routines and then instantiate the child classes, which lets you do stuff like put a very generic routine called evaluate on this very high-level thing, knowing that it's going to do something sensible on all the child classes, but the general incarnation of evaluate doesn't have any meaning. Okay, you can't evaluate something until you know what it is you're evaluating, even though that evaluate makes sense for all the different types of things. So there's some things that kind of make sense to specify on a parent, but only make sense to implement on a child class. And for that, we use abstract methods and abstract classes on the parents. Now, this polymorphism, of course, doesn't require abstract. If we had a parent class that it did make sense, there was some sensible evaluate thing. Say we just did want to return 0 or -1, we could certainly implement it here and not do it abstract. But in this case, it's good for him to do it abstract, and it introduces the whole concept of abstract.
Couldn't you just put the code from evaluate and up node into your X node?
Well, you couldn't, because when you're doing this call, you actually have two evaluate routines. You have this one and this one. If I took this guy and put it in here, how do I ever get the leaf node values out? Right?
Because that would be a child of the...
Yes, but if I had an evaluate routine that looked just like this, okay, over here, it would eventually branch on its left and right members until one of these guys turned out to be null, and in that case it would bomb. All right, because expr node, our op node, is guaranteed because of the nature of its constructor. It's guaranteed to always have a left and right child. Expr nodes can either be op nodes and have children, or they can be children, or they can be the leaf nodes themselves. So this algorithm works nicely here, and this algorithm works nicely here, because this is actually doing an internal switch. This, if you really look what's going on, it's kind of doing a if type equals op node, call op node, call the op node routine. If type equals lit node, call the lit node routine. And it's just saving you from having to write that.
So if you never found into null, then you...
Oh, well, then you would have an infinite tree, though, right? If you had an infinite tree.
Your lit nodes don't have children.
Have
like...
Right, but over here, I don't have any notion of lit node, right? Unless I'm explicitly doing a test. Here, I'm never testing for whether this is just I'm treating as the high-level expr node. So you can carry this concept a little bit farther. One of the things that polymorphism does, one way you could think of it, is as replacing a switch statement where you are switching on a type and then doing something type-specific. And here, yikes, I have crudded up my beautiful code. If, else if. Here, you notice, we are doing exactly that. We are switching on something and doing something different. So if we wanted to be tedious or cool, we could basically subclass op node now and make a plus node and a times node. Okay, and the evaluate routine for plus node and times node is just going to do to this. You know, you won't have to, you can replace this branch so that the plus node would only do that part, the times node would only do that part, and you know, this guy, this evaluate would then be abstract. You could certainly do it that way. At some point, you know, you have to say enough is enough.